Hey everybody, welcome to another awesome earth science video. Today we're going to be talking about mineralogy. We're going to be talking about all the aspects of minerals that you're going to be covering in class, definitions, groupings, a little bit of structure, all the stuff that you need in order to understand this unit so that you can do better on tests. Okay, we're going to be having lots of cool visuals. You're going to see them all around the screen on the PowerPoint that's going on in the background. See my little floating head here. And let's see if we can have a little fun, learn a little stuff. Alright, let's go. So, if we're talking about a mineral, we have to come up with a definition. So, a mineral is defined as a homogeneous, naturally occurring solid, okay, that is compositionally uniform. So, what does that mean? Well, let's look at it. Homogeneous. Homogeneous means that the mineral is made up of exactly the same thing throughout the entire sample. It cannot have random stuff mixed in. So for example, if we look at this picture right here, here we have a probably piece of siltstone that has an impression of a leaf fossil. If we look at this particular substance, it is not the same throughout the entire thing. There are mixtures of different materials in it. The fossil would have left aspects of itself that would make the substance compositionally not uniform. So there's an ununiform sort of structure here. Whereas if you look here, this is pure quartz sand. Everything in this sample on the right hand side is exactly made up of exactly the same thing. So you have to be able to look at this and see the difference between these two. So this is the portion of the definition where we're talking about it being compositionally uniform. Now, next part of it is it must be both naturally occurring and solid. Okay? So, if our substance does not fulfill these two things, it is not a mineral. It might be naturally occurring, but it might not necessarily be a mineral. For example, here we have possibly oil, maybe natural tar coming out of the ground. This is a natural substance. Oil, petroleum, tar, such as you'd see at the La Brea tar pits in Los Angeles, is naturally occurring. And while for economic purposes we may refer to it as a mineral resource, in terms of geology we would not refer to this as a mineral. This is a naturally occurring substance, but since it exists in a liquid and not a solid form, we cannot consider it. Also, if you have something like this, okay, here's something that exists in a solid form. These are chips or a solar panel. I'm not quite sure which one it is, but all the things in here are man-made. So if you're looking at this man-made structure, this is not naturally occurring. It does fit the solid, but it doesn't fit the naturally occurring. Whereas here we see a pretty ruby. This ruby would most definitely hit that part of the definition in terms of being naturally occurring and being solid. So the ruby that you see in your screen right now, definitely a mineral. The two other things, the tar and the image on the left-hand side, are definitely not minerals. Okay? Second, you must be inorganic. What does that mean? It means it must not contain complex hydrocarbons. So you're just going, well, what the heck does that mean? Well, once again, this is a chemistry aspect, okay? If we are talking about a mineral, that mineral cannot contain carbon and hydrogen in any large perceivable amounts. It might be able to contain carbon, it might be able to contain hydrogen. Most things are going to contain at least one of those two, but it cannot contain what we would consider to be organic compounds. Also, if it has carbon, hydrogen, and oxygen, it's almost definitely probably going to be out. Okay, so anything that came from an organic source, primarily something that was either produced from or was originally alive and become petrified and things like that, would not be considered a mineral. So for example, if you're looking at something like lignite, which is one of the stages towards becoming coal, for example, it's wood that's become petrified, and some of the organic stuff has been replaced. Okay, and the water has been taken out by compression and things like that. This image right here would not be considered to be a mineral. Okay, does that make sense? So right here, this image right here that you're looking at right here would not be considered to be a mineral because it has large amounts of hydrocarbons in it left over from when this used to be part of a tree. Okay, next part, if we're talking about minerals, is you have to have what we call a crystalline structure. What does that mean? That means that all the atoms have to be organized in a very specific and geometric and repeating pattern. They can't just be all over the place. They can't be frozen in place. There has to be a repeatable pattern that is showing up over and over again. So for example, if you look here, you see a sample of obsidian. Obsidian, while it is a naturally occurring solid, okay, is what we call volcanic glass. This structure up here is produced when you get a blob of lava that gets shot out of a volcano and it cools like that. When it cools super, super fast like that, the atoms inside basically get locked in place, they get frozen in place, and so they form this structure that we would call obsidian. Obsidian is naturally occurring, it is an igneous rock, but it does not really fall under what we would consider to be a mineral. It has to have the crystals inside of it located in a geometric pattern. So if we're looking over at these guys as they go up here above our screen, okay, you see that you can clearly see all the different geometric patterns that you have and all these different things. Okay, if you're looking at these right here, you can clearly see how this would be a regular geometric pattern. If you were looking at here you can see all the different shapes that we are typically used to. And obviously, if you look at the one that's right behind my floating head, okay, you can see that it does have a repeating pattern that is showing up over and over and over again. Okay, and see, here would be some of the crystal systems that you might be able to see. We have an isometric, a tetragonal, orthorhombic, all these different shapes. These are just geometric patterns that will repeat over and over, both internally, and if the crystal is given long enough to cool, you can actually see it on the external substances and the external minerals themselves. You'll see it in the large scale shape, which you can see in the different crystals that you have down here along the bottom of this particular slide. So let's keep going. So what else do we have? So a mineral must have a specific chemical formula. What does that mean? That means all the atoms that make up that particular mineral must occur in a specific ratio. So if you have hydrogens and oxygens and carbons and silicons, each one of those individual elements has to have a specific ratio in the thing. So for example, if you think back to your bio days, in carbohydrates, right, you always have a 1 to 2 to 1 ratio of carbon, hydrogen, and oxygen in simple carbohydrates. So for example, glucose, C6H12O6. 1 carbon, twice as many hydrogens, same number of oxygens as carbons. That's the ratio. H2O, 2 hydrogens to every 1 oxygen. That is the ratio that we're looking for in the formula. Okay, so if you look, for example, at something like quartz, quartz has a basic structure of SiO2. So what does that mean? That means you have a silicon and oxygens that occur in a 1 to 2 to 1 ratio. Okay, so every silicon, for example, is connected to 2 oxygens. Okay, so you'll have this pattern happen over and over and over again. Now, there's a little wiggle room that you can get. Minerals can vary somewhat within a specific and well-defined limits. Okay, we have figured these things out. So for example, if you have something like olivine, olivine can vary in terms of what does it have. So you can have something like magnesium or iron, that's why those two things are in the parentheses there, okay, and then silicon oxygen 4. Okay, see the little 2 outside of the parentheses? That means you will always have 2 magnesiums or 2 iron, and then you'll have that other compound, the SiO4. So it'll kind of exist within kind of a well-defined sort of ratio that you can use. So if you're looking here, here's your example of quartz. Quartz will always have that silicon bonded to the 2 oxygens in this format that you see over here in this structure. Okay, the olivine that you see here would be the example of what we were talking about before. We could have either the iron or the magnesium bonded to the SiO4. So now that we have this definition of what a mineral is, we know what minerals are, what they aren't, we need to figure out, okay, so we've got all these minerals. Your teacher is going to be showing you all these minerals in class. How do we tell them apart? How do we tell what one mineral is and what another mineral is? How do we, know that this one is olivine and this one is quartz and this one is anhydrate and this one is a sulfate and all these other things? How do we tell them apart? Well, the way we do that is that all minerals have properties, just like anything else. Okay, I have properties you can tell by me: hair color, skin color, height, weight. Okay, attractiveness, lots of different things. Okay, and minerals have them too. Some of them are awesome; they're super useful. Some of them, not great. We can use them in some cases and not in others. Some of them have like unique characteristics that make them really easy to figure out. So when you have to do something like a mineral identification lab, which you're probably going to have to do in class soon, they might be useful. So we'll start off with some of the properties that are okay and some of them that, we'll move through them. Some of them will be great, some of them won't be. The first one is kind of an property, and that is color. Okay? And much like with people, you shouldn't judge minerals by their color. Color is the least useful. Why? Because if you change just a little bit, a slight impurity, you slightly alter the chemical composition of a substance, you can change the color completely. And it can still be quartz, but it'll be a slightly different shade of quartz. Okay? Or it formed in an environment and for some reason water came into the environment at some point and added a new element in that wasn't there before, and so it slightly changes the color. So for example, if you look at different minerals, they can have very different colors, and if you have minerals, they can be completely different minerals and have very similar colors. So you can't really use color as a good identifier. One of the best examples is these 4 or these 3 minerals that you see here in front of you. The purple one, the kind of yellowish golden one, and the orange one. Technically, all of these are types of quartz. Okay, you have amethyst, honey quartz, and I forget what the one on the bottom is called. But these are all forms of quartz. The difference is the presence of a slightly different element as each one was cooling out of the magma that it was forming from. But technically, in a sense of mineralogy, these are all your quartzes. Then you have these two. Okay, these two golden minerals, very pretty, very shiny. If you looked at them and you picked them up, you go, oh my god, I found gold. This is obviously the famous example of iron pyrite and actual native or natural gold. They can be very difficult to tell apart. They look very similar, but there are some tests. You also have things like rubies and sapphires. Rubies and sapphires are both versions of a mineral known as corundum. The difference is this slight presence of things like iron and different elements like that slightly tint the color just a little bit. But technically, on a chemical standpoint, they're roughly the same substance. Next property of minerals that we're going to talk about is what we call luster. So luster is the shininess. It's the easiest way to explain it. It's how shiny a particular mineral is. Okay? If you hear the song from Moana, me too. Okay? But when we're talking about how shiny something is, we want to talk about the quality of light reflected from the surface of the mineral. Basically, when light hits that mineral and comes in, how does it bounce back off? What is the nature of that? It's not always exactly the same. If it hits that particular mineral, bounces and comes back and shines off like a finely polished piece of metal, we refer to it as having a metallic appearance. Okay? If it doesn't have that, we usually use the term non-metallic, but that's not really the greatest one either. Because when we're talking about non-metallic, there are lots of things that are not metallic, but do give off a shine. You could have a piece of glass, that shines a particular way. A crystal. Oil gives a particular shine. A pearl, okay, gives a particular shine. Okay, so we have, when you have thicker liquids, you would refer to them as almost like vitreous, like the vitreous humor in the back of an eyeball has a shine to it. You wouldn't say that's the same shine as you get off a piece of polished steel. You also wouldn't say it's the same as the shine you would get off a piece of glass. So you kind of have to be tricky when we talk about non-metallic. Now, in most cases, in most of your classes, you're going to be dealing with just metallic versus non-metallic. So you're relatively good at using either one of the two phrases that's directly over my head. But when we're talking about more advanced class, an honors class or something like that, you might have to use some of the phrasing that you see over on this side, right over here, okay, in terms of the vitreous or the glassy or the oily or stuff like that. I'm still getting used to this whole YouTube thing, so I'll get better, I promise. Okay, so if we're looking here, we have a typical what we would refer to as a metallic sheen or metallic shine to this, metallic luster. Here you have a sample of iron pyrite. You can see how shiny the light is coming in. So the light's coming in right here. It's hitting it, and it's giving it a nice metallic glow to it. Okay, this would be much more of what we would refer to as a non-metallic luster, although so would that. Okay, you can tell they're not exactly the same. This is obviously much brighter. This one has kind of more of a milkier, softer shine to it, but they are both, you would not confuse both of these with a metallic luster. So both of these would be good examples of what we would consider to be a non-metallic luster. Okay, now the next property is what we call light transmission. Okay, how easily does light pass through it? You have some minerals like the one we just saw in the slide before, where the light you could clearly see it would go right through it. There are some minerals where you can read through it. Pure samples of like Icelandic calcite and things like that. You can see beautifully through them. You can read through them. They have some interesting properties as the light goes through them in terms of refraction and things like that. And then there are other minerals that, it's not the greatest. So here you have a sample where the light, obviously, if you put a light directly behind here, it would go and stop. Okay, it's not going to pass right through it. It's going to go through it and stop when it hits the back end. You can see the shine, you can see the luster, but it's not nearly as great. Okay, so this would have poor light transmission. On the other hand, you can have some minerals that are opaque, like this. When you talk about opaque, you can clearly see that there is something behind this particular mineral sample. You can't tell what it is, but you can see the general shape. It's blocking out the light. This would be opaque in terms of light transmission. And then you have something that has high clarity, like a really high-end diamond, where you can see straight through it. And in fact, the light not only goes through it, but can also get refracted inside of it. Okay, and so you can get that sort of appearance that's going on in a really well-cut diamond that you see here with high, what we would call clarity. So the next property that we're going to talk about is this property that we refer to as streak. Now this one's going to be really, really useful. Basically what happens with streak is that you take a particular mineral and you drag it across a piece of porcelain. And when you drag this particular mineral across this piece of porcelain, it's going to powder and going to leave some residue. Now, you usually go, oh yeah, how's that going to help? Well, sometimes the residue matches the color of the mineral that you see, which isn't great. But sometimes you get these minerals that are light colored and leave a dark streak, or dark colored and leave a light streak. Okay, some of them leave very distinctive streaks. For example, some minerals leave like a greasy gray streak. Some minerals leave like a hematite would leave a bright red streak, and so those can be incredibly useful for identifying those particular. So basically, it's just a mineral in its powdered form. You take a piece of porcelain tile, and you just kind of rub it along there. And when you rub it along there, it's going to powder and leave this residue. Okay. Usually, typically, when we talk about this, we do use a light colored streak plate like you see in the slide right over here, okay? But sometimes you do use a darker one, which you see in the slide, okay, just above my head, and that would be useful to see a white streak, okay? Now, sometimes you'll see a white, sometimes you'll get nothing, it'll be a colorless streak. You can record that as well. If you look on your reference table, depending on where you are, you will see that streak is incredibly important for identifying the different minerals, and when we do the video on the mineral identification lab, that should definitely help you to identify them as well. Okay? Now, an incredibly useful trick for figuring it out, and in order to do this you have to have kind of a discerning eye, is what we refer to as crystal habit. That is the common crystal shape for a particular mineral. Now, some minerals have just one crystal habit. They always grow the same exact way. When they cool, they always grow in blocks, or they always grow in pyramids, or they always grow in hexagonal prisms, or things like that. Some of them can have multiple habits. This is just a kind of thing that if you happen to have a rocks and minerals guidebook or field book, you can use that to identify any particular habits that might be important for that. So for example, if you have a rocks and minerals guidebook, kind of like this one, okay, this one's going to give you lots and lots of the different structures that you would have, lots of the distinct crystal habits that you might have. So for example, if you look at these pages right here, okay, you can see that some of them will have the different crystal habits that are found. For example, you see right there the crystal habit that you have right there, okay? That would be an example of a particular crystal habit that you might have. Like I said, most minerals are going to tend to have one particular crystal habit. For example, garnets and halite always form crystals in a very specific shape, but sometimes you get multiple ones in things like pyrite. Sometimes you don't get a clear-cut geometric shape, but they have very unique shapes. They look like bubbles, they look like dinner plates, they look like fangs, they look like fibers, and those can be really, really useful in order to identify it. So for example, here you have a sample of garnet. These are garnet crystals. You can see that they form a definite prism, a geometric prism that repeats over and over and over again. The longer it has to cool, the bigger these crystals are going to be. Okay, here you have a sample of halite. You can see the nice rectangular or quadrilateral prisms that they're forming over and over again. Okay, this would be a sample of pyrite where you could see a couple of different shapes, but they do repeat on multiple purposes. This would be an example of a crystal that is non-geometric. It's almost like a geodesic dome sort of forming, or like a bubble here. And then this one's just really cool. It looks like little dinner plates that are all stacked one on top of the other, on top of the other, on top of the other. Okay, all of these would be incredibly useful in order to identify a particular mineral. So you want to look for the shapes of the different crystals that you have in whatever mineral sample that you're looking at. Try to get an idea, look at these things and see what's going on there. So the next property we're going to talk about is tenacity. So tenacity is a mineral's ability to resist breaking or deforming. Basically, it's how easily does something bend, okay, and not break. I'm not going to snap the fingers off. And this is primarily linked to how the different atoms in a particular mineral are bonded together. As some of your teachers may have explained to you, you have different types of bonding. We have what we call ionic bonding. We have covalent bonding. Ionic bonded minerals are held together because one thing basically steals an electron off of another thing, and so one thing becomes positively charged, the other thing becomes negatively charged, and they kind of attract each other, but don't lock together. And since they're just kind of attracted to each other, because one thing stole something else from the other one, the bond between them isn't the super tightest in the world. It's there and they'll hold together, but there's a weak spot. Okay, if anything applies enough force, they can just snap apart from each other. If you have what we call a metallic bond, which can exist between things that exist in what we call the D block of the periodic table, which is that center section where one metal bonds with another metal, those things tend to be malleable. What does that mean? Since they have what we call a sea of electrons and there's some unique properties that are going on there, those things can tend to just kind of like bend really, really easily. This is why if you think of pieces of metal, you can easily bend them and stuff like that into different shapes. Okay, and so we see this in a lot of different minerals. Okay, sometimes you can have what we call things being sectile, which would be a type of tenacity, where you can cut things into shavings. This would be things like gypsum, which is what you find in stuff like drywall. You can like shave it down into thin little sections of it, little shavings that you see. Okay, you can have elastics that can be bent super, super easy, and this would be things like mica. Okay, this is a sample of mica you might have seen in class. Mica can bend really, really easily. And originally, micas were actually used as the original glass in a lot of window panes in things like medieval castles and the like. The next property we're going to talk about is what we refer to as hardness. So hardness is an object's resistance to abrasion or scratching. What the heck does that mean? Okay, it's basically how difficult it is to put a mark in it, to scratch something. Okay, when we look at this, okay, what we basically have is this scale that was created many years ago called the Mohs scale of hardness. Okay, and we take a mineral and we see how different minerals on this that have already had a predetermined scale of hardness, do they scratch it, or does the mineral in question scratch that? So if you're looking at the screen right now, okay, over here you will see all these different minerals that we have on one side of the particular graph. We have diamond being the hardest one, which is Mohs scale number 10, and then talc all the way down at the bottom being Mohs scale number 1. Okay, so when we're looking at this, and then you have the common objects there. For example, a masonry drill bit is about 8.5, a steel nail is about 6.5, a knife or a piece of glass are about 5.5. You have your copper penny and you have your fingernail. Okay, right between about these different values that you see on the graph over here. So what we basically do is we would take a sample and we'd say, okay, does it scratch talc? If it scratches talc, it's harder than 1. If it doesn't scratch talc, then it's less than 1, which is rare. Okay, and so you'd work your way through this and you say, does it scratch it or does it get scratched by it? And you play around. Now, there are obviously more technical ways that we could do this, but for example, in your mineral identification lab, you're going to have a group of these, probably up to about quartz, maybe corundum, depending on if your school has these particular things. I doubt many of you are going to have diamond, although maybe some of you have a diamond tip structure that your school might be providing, and then you can test that one out. But basically, you're going to keep testing one for another and say, okay, here's my mineral. Does it get scratched or does it scratch? You do the test and see what's going on and try to figure out where it goes. If you're looking at the chart that your teacher will be giving you, you're going to try to fit it into the range of where it might be. Once again, incredibly useful tool if you want to be able to figure out exactly what is going on with one particular sample. Next property we're going to talk about is cleavage. Keep your minds out of the gutter. Okay, when we talk about cleavage, basically it's the tendency for a mineral to break. Okay, so the mineral is actually breaking, okay, along a particular weak point of bonding. We call that cleaving. Okay, so when we talk about cleavage, what do we mean? We mean that the mineral, whenever we strike it, it always breaks the same way at the same angle. It could be a 180-degree angle, it could be a 120-degree angle, it could be a 60-degree angle, 40-degree angle, okay, or some combination of them. Okay, typically this is going to happen when you have mixtures of bonding, but it'll usually cleave along the points of ionic bonding because, like we said before, that's where you're going to have your weakest connection between two particular groups of molecules or elements. If it's bonding, it would be between elements. Don't kill me in the comments. Okay? Now, when we look at this picture here, you have the different types of cleavage you can have. So you can have cleavage in one direction. When that happens, what does that mean? That means that your substance always breaks into like flat sheets. Okay, so you're typically going to get this in micas, like you see in the chart above me right here. Okay, all the way at the top right here over my head, you can see the muscovite that always breaks into these flat sheets. You can break into two directions at 90 degrees, which means you have nice right angles. Okay, and you get these nice sharp right corners, like the feldspar that you see right over my head as well. Okay, you can break at at 2 degrees or 2 points, but not at 90 degrees. So you can have some obtuse angles and some acute angles, like you would see. It's flowing behind my head right now. Okay, we'll make sure that you can see that. And you're going to have lots of different combinations of that you have. You can have three, where you get a cubal break. You can have a rhombohedral break, like in calcium. You can have an octahedral, like in fluorite, which is what's behind my head right here. Okay, so there are lots of different combinations of different types of cleavage that you could have. If you follow the chart once again in the lab that you're going to be doing, this is going to be important. So you have to look at it. You might have to use a magnifying glass to be able to see what's going on, but you want to look for where the different breaks are in the different minerals that we are talking about. Okay, now not every mineral is going to cleave. Sometimes you'll have things that are almost exclusively held together by covalent bonds. Covalent bonds are where you have two atoms, and instead of one thing stealing an electron off another thing and then them getting positive and negative and dragging each other around like this, they will share electrons. And when they share electrons, you're going to get a bond that's much, much tighter. You see, if I try to pull this apart, it's going to be much, much harder to rip these two particular atoms apart. So when you have two atoms that are so tightly linked, I could break it, but I'm going to have to put a lot of force into it. But it's just going to break along wherever I put the most amount of force. And so you're going to get this kind of uneven breaking pattern in the mineral. Okay, where you kind of have that uniform bond strength because you tend to have that covalent bond all over the place. So something like quartz tends to show this pattern. This is what we would call conchoidal fracture. Okay, and you can see here where it breaks like pieces of glass. Okay, quartz is going to do this because, like we said, quartz is almost exclusively held together by a covalent bond, and so you're going to get this uneven pattern. You don't see anything repeating over and over again. There's no clear-cut angles that you can measure over and over again. A very useful tool. Figure out, does it cleave or does it fracture? What you're looking for is repeating, usually flat or smooth surfaces over and over again. That's going to be an indication of cleavage. If you have these uneven, unreproduced surfaces, then you're probably looking at something that is fracturing. Specific gravity. Specific gravity is an experiment that your teacher might have showed you, and it basically says that the ratio of the mineral weight equal to an equal value of water. Your teacher may have shown you this where they took a particular sample and they hang it and they put it in a container of water and it'll displace an equal value of that amount of water. Okay, most minerals tend to have a specific gravity that is much, much higher than that of basic water. The specific gravity of water we basically assume to be right about 1. So most have a specific gravity of between 2 and 3. But there are some that have very high ones. For example, iron, pyrite, and gold have very different specific gravities, and that's a useful test in order to see, which one is which. Gold tends to be much, much denser, much, much heavier, and you can feel it. It tends to, have more of a heft to it. That would be the best way to describe what we mean by when we're talking about specific gravity. So some minerals have unique properties. If you get one of these and you can figure out this property of it, it makes it super easy to identify and you should be able to bang it out real fast. One of these is magnetite. Magnetite is a natural magnet. If you take anything that has iron in it, it will naturally stick to it really, really easy. So you might have little bits of iron filings or a little bar in your identification kit. If it'll stick to the mineral, boom, you've got magnetite, move on. Taste. Halite tastes incredibly salty. It is like basically, somebody dumped half a thing of table salt in your mouth. While I'm not recommending that you taste the minerals, you can. If your teacher says it's okay, ask, obviously, because some minerals are poisonous, so you don't want to go around licking anything in the lab. But halite has this incredibly strong salty taste. And then there are some minerals that will fluoresce. So what does that mean? They will glow unique colors under certain wavelengths of light. Example of this would be something like willemite. Okay, and then to throw one other one in, something like sulfur has an incredibly pungent smell. If you take a little bit of water and rub it on it, it will stink like rotten eggs. Okay, so if we look, this is the magnetite. Here you can see these paper clips are sticking to it. If you get this, boom, you're good, you're great. Here you have two girls doing what I said not to do, but if you lick it and you're in the field, you could probably tell and figure out if there is a sample of halite. These would be some of these minerals that have this natural fluorescence that we talk about, willemite and things like that. And this is actually a sample from a mine in Ogdensburg, New Jersey, where I took this actual picture of myself of some of these fluorescent minerals that you have. And this is the cave wall that I took a picture of, and you can see how they are glowing these different colors. Okay, so these would be some properties that if you get these, boom, you should be able to identify them really, really fast. Now, of all the minerals that exist out there, what are we going to do with them? Well, we do what we typically do in science. We tend to classify them. We tend to group them together. So when we talk about putting the minerals together, okay, in general we tend to kind of try to stick them into what we call the rock forming groups and the economic materials. Now we're not going to focus too much on the economic materials, but those would be like, for example, the minerals that are important for making drywall. So for example, gypsum, like we had mentioned before, is super important for making the drywall that you might find in your basement or the walls of your house. Copper that we use for wiring has to be extracted from things like malachite. The steel that we have that's in our buildings has to be, the iron has to come out of like the banded iron formations that we find all across the planet. Now, of all the elements that exist on the periodic table, and there's a lot, there are only about 8 of them that we find in a relatively high abundance in the crust of the Earth. Okay, so those 8 elements make up about 98% of the crust. It's slightly different in the mantle and obviously the core. But for the crust, we've got about 8 elements. That would be your oxygen, your silicon, your aluminum, your iron, your calcium, your sodium, your potassium, and your magnesium. Now of these, silicon and oxygen make up 72% of the crust alone, usually combined into the form of silica. And so we call any mineral that contains this silicon and oxygen silicates. We also have carbonates, halides, oxides, sulfides, sulfates, and what we call native elements. We'll talk about these groups in a second. Okay, so if you're looking at this chart here on the screen right here, what you're going to be seeing is a typical pie chart detailing what you have. So here you see you have oxygen that makes up a large percentage of the crust, almost 50% at 46%. Silicon's over here, making up about 27-28%. Then you've got iron, potassium, magnesium, okay, sodium, aluminum, okay, and then your other elements is this tiny little sliver right here. So your big 3, if you're just looking at the 3 right here, are going to be silicon, oxygen, and aluminum. Okay, and then all the other elements, we have them, but in very, very, very rare numbers do they exist on the crust of the Earth, or in the crust of the Earth, I should say. So when we talk about these mineral groups, like we said, we're going to start talking about the silicates. So the silicates all contain oxygen and silicon in a very specific shape called the tetrahedron. Okay, a lot of these silicates are going to tend to have some other common elements, so an aluminum or potassium or magnesium, but they can occasionally contain some of the other rarer elements. Now, this silicate tetrahedron is such an important, and it's such a strong structure that it can form a huge amount of the minerals that we find on the surface of the Earth. Okay, we can have them existing in a bunch of shapes. You can have little individual tetrahedron, they kind of look like little pyramids. Okay, we can have tetrahedrons that are bonded to other tetrahedrons, in long chains. They can exist in sheets. They can exist in long polymers, which are enormous chains. They can have a weird 3D structure. Since we have so many possible combinations, that allows us to have a huge range of different silicates that we can work with. So right here you'll see this is your standard tetrahedral structure right here in actual space. Okay, but here you would have the silicon forms kind of the center of the pyramid, and then you have the corners of the pyramid would be these 4 oxygen molecules that are bonded to this silicon molecule. Okay, and so over here in this picture you can see you have a couple of independent tetrahedron right here. Okay, and then you have a single chain where the tetrahedron are bonded just one. They share one oxygen, one oxygen. Okay, here you have a double chain. There we would have a sheet, and this would be a 3-dimensional framework. And so you can get these really, really complicated, convoluted forms of these various different molecules and these various different polymers and these various different minerals. Okay, so for example, if you have like single tetrahedron that are just kind of hanging out, you can get something like an olivine. Okay, when you have single chains, you'll get stuff like augite, which is a type of pyroxene. Double chains will give you hornblende. Biotite and muscovite mica would be these sheets here. Quartz and feldspars would be these 3-dimensional shapes that you see right here. So there's a lot, and obviously this is just a small little microcosm of all the silicates that can exist out there. But the silicates are super important, right? Quartz we use all the time, major ingredient in window glass and things like that. So there's a lot of pieces of evidence that we have here, and a lot of pieces of data that we have here that we have to analyze for this. So when we look at the silicates, which are the primary form of mineral that we talked about, are primarily formed when you have molten rock, whether that be magma deep beneath the Earth's surface or lava as it comes out on top of the Earth's surface and it cools. So you can get a variety of different minerals that are going to form if you have low temperature and low pressure close to the surface, or high temperature and high pressure way down below the surface, and everything in between. Also, whatever is in that particular magma or lava is going to affect what comes out in terms of the minerals that are formed as it cools. When we talk about the silicates, we divide the silicates into two main groups. We have the light colored silicates, which we call the non-ferromagnesiums, and the dark colored silicates, which we call the ferromagnesiums. So here you have an example of a light colored non-ferromagnesium and a feldspar. Okay, and here we have a darker, what we would call a ferromagnesium mineral. So when we talk about the silicates are broken up into two main groups. One group is called the non-ferromagnesians. So the non-ferromagnesians are a group of silicates. These are still silicates. These things tend to be light in color. They tend to have a relatively low specific gravity, around 2.7. And they tend to have a lot of aluminum, potassium, calcium, and sodium. Those tend to be the metals that you tend to find in this. That also tends to give them the lighter color. What they tend to lack is a lot of iron and a lot of magnesium. Okay, that also tends to give them the lighter specific gravity that we were talking about. When we look at the non-ferromagnesiums, they're broken up into a couple of different groups. So we have our feldspars, our quartzes, our muscovite micas, and our clays. Okay, so if we're talking about feldspars, the first group, these are the most common mineral group on the planet. They form underneath a huge wide range of temperatures and a lot of different pressures. That means that they can form, all across the crust, all at all different points in the crust, where the crust is at various different temperatures and things like that. Okay, they tend to have a hardness of about 6, so they're softer than quartz and things like that, but still relatively high in scale. They tend to have cleavage at about 90 degrees, which means it's going to make those nice sharp right angles. And they tend to be glassy or pearly in luster, so this would be a non-metallic luster. Okay, and they tend to shine like that, very similar to kind of like polished countertops. Good way to kind of understand them. So the two main features of feldspars, or the two main types of feldspars, are plagioclase feldspars, which have lots of sodium and calcium, and potassium, or the older word is orthoclase feldspars, which have lots of potassium ions in them. So the difference you're looking here is sodium and calcium ions versus potassium ions. Okay, and that's going to lead to them having different colors. Plagiocases are usually white to gray, and potassium feldspars orthoclase feldspars tend to be like pinkish to orangish in colors. So right here you have an example of a plagioclase feldspar. Okay, you can see the striations. That's a key indicator that you're also looking at, these lines that you can see on the screen. Okay, these sharp lines right here, these striations would be an indicator that you're looking at a plagioclase feldspar. And a potassium or an orthoclase feldspar is going to look like this. Okay, much smoother, lighter in color in terms of, well, not lighter, but more like peachy to pink in color. Okay, and you do not see the striations. That's going to be the key thing you want to look at if you're trying to tell the difference between plagioclase and potassium feldspars. Remember, potassium feldspars are also referred to as orthoclase. The next group of silicates that we're going to talk about are quartzes. Quartzes is the only silicate material that consists almost entirely of silicon and oxygen. Usually it's pure silica. So those little packets of silica that you get in your deliveries and clothes and stuff like that tend to be little bundles of quartz that they put in there, or just pure silica that they throw in there. All the bonds are covalent bonds, and this gives you a very hard, a very durable mineral. Quartz is used in a lot of things. It's used in timepieces, it's used in glass, it's used in a lot of things that you want. Pure quartz tends to be very clear, gives you a nice hexagonal six-sided crystal. But occasionally you do get an impurity, and when you get an impurity, you're going to tend to get a color. So you're going to get things like an amethyst or a smoky quartz or a honey quartz that we saw earlier in the slideshow. So on the screen right here, you can see right here, this would be your pure quartz with no impurities in there. Nice hexagonal crystals. Here you have your amethyst. Okay, that has some of the impurities which give you that pinky color. This is your smoky quartz here. Okay, much darker color, and you have another one here that also has impurities that are giving it this orange color. But technically, all four of these minerals that you see in the screen right now would all be quartzes. The micas, okay? The micas tend to be shiny and clear. When you're looking at them, they tend to be very almost like thin little films. And the easiest way to tell them apart is their cleavage. They literally break off into thin little sheets. Muscovite micas tend to be almost transparent. They're very, very light colored. They tend to go from like a clearish to a very light green, very smoky sort of greenish color. Okay, you can quite often find them if you look in your countertops at home. You probably have mica. Those would be the little flecks that almost look like sparkles, like somebody sprinkled little bits of sparkles or little bits of glitter inside your countertop. That's typically the micas that you're looking at. So this is what it looks like. You can see thin little sheets. Okay, the light, a lot of light transmission able to go through them. So you know, and the identifiable part is that you can see all these flat little sheets. And when you're looking, all the little shiny spots that you see in here that give this kind of the glittery appearance. Your countertop, like I said, might have this. All those little bits of rock glitter are going to be your micas. That's what you're looking at here, specifically like your muscovite micas and stuff like that. Clays. Clays are silicates that tend to form that sheet structure, so lots of the tetrahedron growing together and growing those large flat sheets. Okay, and a lot of times they tend to come from the breakdown of other silicates. The reason that clays are so important is that they tend to be a major component in a large amount of soils that we would use for different purposes, agricultural and whatnot. They're weak bonds, which is why when you wet clay, it gives you that kind of weak, that slimy texture. Everybody knows, like when you put like clay between your fingers, it has a very unique sensation between your fingers. And so the weak bonds that are in the clay tend to give you that sensation. One thing about clays is they tend to be able to absorb large amounts of water, so we're going to tend to find them a lot of times when we're talking about things like aquifers and groundwater and things like that. They're going to be critically important. Okay, commercially, one of the clay minerals that's important is this mineral called kaolinite, and kaolinite is actually used a lot of times in textbooks. It gives textbooks kind of that glassy sheen, that waxy appearance that can help. So if you drop some water on one of the pages in a textbook, it doesn't immediately change like a piece of loose leaf or a piece of paper would. It doesn't just eat through the paper. It doesn't completely wreck it. It actually allows the water to bead up and kind of slide down a little bit. So this kaolinite is super, super important as an example of a clay mineral in terms of a commercial matter. And this would be a picture of clays. Okay, we typically see this. You might see this on the sides of roads and things like that. Very, very important. This would be a sample of kaolinite, like I mentioned before. So they break this down and they add it to the pulp while they're making pages, or they add it to as they're producing the textbook. Once again, to give it kind of that waxy appearance. So the next group of silicates that we're going to talk about are the ferromagnesians. Ferro, anytime you see this is a good trick for when you get to chemistry. Anytime you see this term ferro, you are talking about iron. Magnesium. So these ferromagnesians are going to contain lots and lots of ions of iron and magnesium in their structure. This tends to give them a much darker color and tends to make them have a much, much higher specific gravity, so they tend to be much heavier. Minerals, rocks that have a large amount of these ferromagnesian minerals in it tend to be incredibly dark. So the basalts that you see on the screens up here, okay, that form from this lava as it cooled, this lava rock, are going to tend to contain a large amount of ferromagnesic minerals in it. There are lots of different groups of ferromagnesians. Once again, starting with like simple tetrahedron, individual tetrahedron. So that would be things like the olivine that we saw before. Olivines tend to form at very, very high temperatures. We tend to find them, it's going to be one of the major ingredients, for example, in like the mantle of the earth. Those rocks tend to have large amounts of olivine in it. Magmas that tended to form a long time ago, when the earth was much hotter, are going to tend to have had a lot more olivine in it. We do get it sometimes on the surface of the earth. And the colors can be from black to olive green, which makes sense because they're like the olives that you would find, that people eat to this day. Members of the olivine group tend to form about 50% of the minerals in the upper sections of the mantle. So if you remember from the beginning of the year, you have your crust at the top, then you have your adenosphere, which is your upper mantle, and the bottom layer of the crust. So that area tends to have a large amount of olivine in it. This is a sample of olivine, very appropriate, a green crystal like this. Okay, and this is going to be a major ingredient in a large amount of very high temperature magmas. So when they cool, those magmas are going to tend to give you these particular minerals. Garnets are birthstone of January, I believe. Once again, they are individual tetrahedron where you link one tetrahedron to the other one by the use of metallic ions. Okay, we tend to find them a lot in metamorphic rocks. If you go upstate, a lot of the Adirondack Mountains, which are mountain ranges that have existed for well over 1 billion years and have been put under huge amount of stress as the plates have moved around, you tend to find very, very large garnets all around upstate New York and any regions where you have large amounts of pressure that causes metamorphosis, what we would refer to as like regional metamorphosis, not necessarily contact metamorphosis. We'll get to that when we do metamorphism later. Okay, but areas where you have mountains that have been folded and things like that, you're going to tend to get the formation of these large garnets. If you go to the Grand Canyon, for example, and you go down to the basement rocks that are down at the bottom, what are known as the Vishnu schist, they tend to have very, very large garnets in them as well, and that's one of the indicators that these rocks were put under a huge amount of pressure over a long period of time. So this is an example of a garnet. Now the garnet specifically, the ones that we're looking at are these reddish crystals that you see here. Okay, very large, very pretty. One of the reasons that they're probably a birthstone. But like we said, you tend to find them in the rocks that have been put under a heck of a lot of stress over the years. The pyroxenes. Pyroxenes are typically dark green to black in color. Some pyroxenes tend to vary depending on the impurity that they have to a light green to white. It's not very common, but they do tend to be much darker. They tend to have cleavage in two nice clear-cut directions. Okay, and they quite often will form right around the volcanic vent. So wherever you have large amounts of magma escaping to turn into lava, you're going to tend to get the formation there. As that cools, you're going to tend to get a lot of pyroxene minerals forming there. This would be an example of pyroxene, which would be these darker crystals that you see here. Okay, and you can right here you can clearly see these nice cleavage patterns that you see at nice right angles right here. You can see them here as well. So you can clearly see what's going on when we talk about cleavage in two directions. You can also see the nice geometric crystals that these things would form. Amphiboles. Okay, I'm going to tell you this now. If you have to tell the difference between a pyroxene and an amphibole, it's some of the hardest stuff to do sometimes. The difference is the angles that you're looking for cleavage. For this case, it would either be 60 degrees or 120 degrees. So you're looking for cleavage at an obtuse angle or an acute angle. So an acute angle or an obtuse angle. Okay, they can be a little tricky. It might take you a little while to get used to it. A lot of times amphiboles will tend to form large crystals. The most common form of this mineral that we find is hornblende. You can see these large elongated crystals here. Okay, and you can see the patterns of the different cleavage patterns that you're going to get, the large crystal shapes that you have here. Once again, like I said, amphiboles and hornblendes, hornblendes, pyroxenes, can be tricky minerals to tell apart. Okay, biotites. Biotites are a form of mica. This mica has a darker, more iron-rich content, so it tends to be much darker, but it's still going to give you that shininess that you got. We find it in granite a lot. Like I said, your countertops are going to tend to have this a lot in it. And these particular minerals are going to tend to, once again, show that kind of like flat cleavage pattern. They tend to break into sheets and things like that, and so it makes it quite useful. They're very easy to see when you're in lab. If you get these flat sheets, the easiest way to tell this one apart from the other mica that we'll talk about in a second is the darker color. Okay, the biotite tends to have a little bit darker color into it, whereas the muscovite is more lightly colored, has that pearly luster, still has the one cleavage plane, and muscovite was the mica that was primarily used, like we talked about earlier, to form windows during the medieval period. Okay, so here we have a sample. Sorry, it's been moved a little bit. You can see it right there. So if we're talking about the minerals that don't have silica, we call those the non-silicates because they don't have silica as a primary constituent. The non-silicates are divided into groups based on whatever negative ion is associated with that particular mineral. So for example, if you have carbonate as your negative ion, which would be CO3, we call those dicarbonates. Example of this would be if you take calcium and carbonate, you make calcite. Okay? If you take some copper and some carbonate, you make this thing called malachite. So if we're looking here we have a sample of calcite. Calcite is a very interesting mineral. It's been used in lots of different cultures for lots of different ceremonial purposes, for lots of different practical purposes. In terms of mineral identification, calcium carbonate can be, or calcite can be identified by putting a small drop of a very weak acid on it, and what it'll actually do is it'll bubble and it'll fizz as it releases carbon dioxide, and that's how you can tell the difference between something like calcite and halite, for example, because they look very similar, although their crystal habits are different. Here you have a really, really cool image of a calcite skull. This is from skulls.com, really cool website, nothing to do with them, but wanted to give them props because that's where the image comes from. Don't even know if they still exist anymore, but you can get a skull carved out of this mineral. It's kind of cool. Here we have malachite. Malachite would be a mineral that has a high amount of copper. Veins of this are very pretty. They're very green in particular rocks that they show up in. And we can have a malachite skull right here. Kind of awesome. The next group of non-silicates that we have are the halides. The halides have a halogen as their negative ion. The halogens would be the group 17 elements. This would be things like chlorine, fluorine, and bromine. And examples of this would be the minerals halite, which is commonly known as rock salt. It used to be the primary form of rock salt that is used to be spread on roads and things like that, although nowadays it's a slightly different composition. And fluorite, which is a popular gemstone, a very pretty stone that exhibits very interesting cleavage patterns. It cleaves in 4 directions at once. So here we have fluorite, very pretty. It gives a lot of light when put under certain spectrum and certain wavelengths of light. Here is, once again, a skull carved out of fluorite, just because look how awesome that looks. Okay, another example of a non-silicate mineral would be the oxides. The oxides would have oxygen as their negative ion. Example of this would be the mineral known as corundum. Corundum is high up on the Mohs scale of hardness. That's where you may recognize the word from. And depending on what positive ion you add, you can actually get very different gemstones. You can get things like sapphires and rubies out of corundum just by tweaking the positive ion that you get out of it. It's a very pretty mineral on its own, but once again, another awesome looking corundum skull that you can get. Just kind of cool looking, amazing looking sort of thing. The next group of non-silicates that we have are the sulfides. The sulfides are going to have sulfur as their negative ion. And the common example of this would be the mineral galena. Galena is an excellent source of lead. Most of your classrooms should have them, although typically they are wrapped up for your protection, as lead can be poisonous. But for extraction purposes, if we need lead for a particular compound, galena was one of the primary minerals that we did use it. It shows excellent cleavage patterns, excellent crystal habits. It's a really easy way to, you can see the cuboidal crystals that you have in there. It's relatively soft, but also dense. It does contain large amounts of lead, but it's a very useful for economic purposes. The next group of non-silicates are the sulfates. Do not confuse the sulfates with the sulfides. There is a difference between sulfate and sulfur. Yes, sulfate has sulfur in it, but it also has 4 oxygens. This will be something that gets really important when you guys go to chemistry and you have to learn the difference between compounds and polyatomic ions, all stuff that you'll do when you get to chemistry or when you watch our chemistry videos. An example of this would be the mineral anhydrite. Anhydrite is primarily found around volcanic vents, and it has a very strong odor of like rotten eggs. It's one of the reasons that a lot of material around volcanic regions does have that rotten, eggy sort of smell. Very pretty. I know certain people that if they were anywhere close to this would have bad allergic reaction. And then we have what we call the native elements. Now the native elements are single unbonded elements that have various economic uses. So this would be like pure copper, pure gold. It's not bonded to anything. These are really, really economically important because if you can get these out, it means you don't have to go through the process of taking them out of something else. So for example, aluminum is primarily found in something called bauxite. That's a mineral. But in order to get the aluminum out, you have to separate the aluminum from what it's bonded to, and that takes time. If you can find a native vein, a vein of just pure aluminum, or a vein of pure copper, or a vein of, obviously gold is very unreactive, so those tend to be found in that way. But that's incredibly economically valuable to us. And so the native elements, anytime we find a vein of pure uranium, if we could find that, would be amazing, because you could just pull it out and use it for exactly what you have to do without having to go through the process of separating it from the other elements or the other atoms that it would be bonded to. So here we have an example of a pure vein of copper. So this would be pure copper. You can pull this out and immediately start using it for whatever you might need. And so that, ladies and gentlemen, is mineralogy in a short version. You could take an entire course of this, but this should basically cover the basics that you need for any earth science class that you might be in right now, give you kind of an overview of the things we're going to talk about, maybe a little bit more in depth in some ways. Maybe there are a couple things that your professor, your teacher focuses them a little bit more on, but I hope this gives you a good background on what we've been doing. I hope you found this interesting. If you'd like, share, subscribe. We'll be doing a lot more of these. I hope this helps everybody. And otherwise, just keep learning, never stop, and we'll see you in the next one. All right, everybody. Peace out.